to introduce Scott Tilley, our guest banquet speaker, B7TIL. He's done some amazing things the last couple of years, and somehow we managed to convince him to come.
Thanks, Dave. I'd like to take a couple seconds to acknowledge Barry V4MA for his kind invitation to come and do something I've always meant to get more involved in. And it's not that I wasn't involved in microwave amateur radio. It's been in my blood since I was a teenager. Barry's invitation kind of like re-emphasized that maybe I need to get more involved in the microwave community. Why? Back in the early or late 1980s, my dad used to drag me to Dayton every year. He's a ham, VA3TD, formerly VE3HSY. And we would go to Dayton every year, and I was VE3TIL at the time, and I'd lug home all kinds of stuff. And one year I went to Dayton with a bee in my bonnet about microwave equipment. So I came home with a whole bunch of gunplexers, a 60 centimeter dish, and a whole bunch of other things, and my dad looked at me and like, what are you going on about, boy? And that has nothing to do with HF. You're not going to talk to anybody on that stuff. And it was a couple of years later I met VE3 SMA, and I had my first 10 gigahertz contact, standing on a little ski hill. Yeah, Ontario has ski hills, in Kitchener-Waterloo. And from there, I finished my secondary education at the time and post-secondary education, and started my career and kind of lost touch with amateur radio for a while. But it came back. Like most amateurs, they have this curve when they're young, they pick it up, it gets in their blood, the addiction begins, and it just kind of it's like one of those kind of viruses that just kind of sits and stews in you. And you get a little bit older in life, you get things moving on, and all of a sudden it comes back and bites you. It says, okay, it's time to pay it back. So part of my payback, it was discovering that I had a dual addiction or a dual virus to astronomy and satellites. And amateur radio, of course, leads to that path. So it took a little while before I had my backyard of my own. And as many of you in this room that have backyards of your own with large apparati, and maybe you don't choose to have it fixed to your backyard, but maybe you got it in the back of your truck or your car. You've got this stuff that you drag around and you look at the world with, and it defines who you are, and it defines your experience with the world. What I'd like to do tonight is share with you guys some of the tales from my backyard, and how amateur radio and astronomy and my view of the world has been altered by it, and how I've been privileged to actually share a bit of that with the world, and how it's kind of reflected back to me. It's been a pretty amazing. I got into satellite tracking about 15 years ago. It started off as a really steep learning curve like amateur radio, and because I live in a rainforest, the radio part of my world came back really quickly, because you can't really see into space at optical wavelengths very well here for probably 9 months of the year. So radio really became an important feature of it, and you'll see that in this presentation. So let's begin. So in the beginning, who was looking into space? Who were the first people to track things in orbit? It wasn't the governments, it was us. So we should be hearing some beeping. You can hear a faint beep there. That's probably a good analogy for things that go beep in space. Sputnik 1 went up. And of course the whole world was, whether you were on one side of the political divide or the other, there was euphoria, and there was also a lot of like, what the hell? And in the amateur world, the Soviet Union did something very wise. They placed the radio beacon right beside WWV on 20 megahertz. And the world heard this beep. And they heard this beep over and over and over again. And the first Doppler analysis happened. And it was all done by amateurs. If you go digging through the literature, a lot of these resources are still available on the web, and the first Doppler curves appeared. The first amateurs started tracking satellites by radio. It wasn't long before This is the rocket booster for Sputnik 1. And that is an actual video taken by a TV crew that had a couple of amateur astronomers that told them where to point and how to actually see the rocket booster. That's 1957, and they pulled out a TV camera with a high sensitivity VidCon tube or whatever the heck they were using back then, and they managed to see a satellite in orbit. Here's the really cool part of this. This video came to my attention from a colleague of mine, Ted Moselcan in Toronto, who's in the amateur satellite tracking community, is a renowned, internationally known person for tracking classified military missions and whatnot. And one of his interests is historical observations. So he goes back through the literature, the media, and everything else, and finds things like this. And what he was able to do is reconstruct the orbit of the Sputnik 1 mission from evidence that we have today of it. And a lot of that evidence disappeared in time. So what Ted was able to do was, using this video and other resources and other observations that he dug up, was reconstructed all of that history. And that history is important to us because not only does it teach us what happened in the past, but those skills that we develop allow us to move forward in the future. So how did amateurs get going? There was this program called Operation Moonwatch. And literally, they weren't really watching the moon, but the idea was the analogy of man-made moons. Sputnik was the first man-made moon. So groups around the world formed, literally clubs formed out of nowhere, and they started tracking the first objects in space. The rocket booster from Sputnik 1, Sputnik 1. Sputnik 2 went up shortly thereafter. There was Vanguard, there was Explorer 1, on and on it went. So the first objects went up, and it was amateurs that were really filling that gap before the government started to spend the money, get the resources in place to be able to provide space situational awareness, 1950s style. By the 1960s, the space program had started to develop further. This is a photograph taken by a colleague of mine, Greg Roberts, ZS1BL. He's now presently a retired astronomer. He was also an avid amateur radio operator and satellite tracker. And his group down in South Africa, they were very active in tracking the space program. There's a very curious thing about being in South Africa at the time of the space program. If you look at a map, Cape Canaveral's up north, and anything being launched has to go dips down over Africa and over South Africa. So they had a perfect front seat view of everything that was being launched into space. All of these first manned missions of the United States, like the Project Gemini, Project Mercury, the Apollo program. So they started building antennas. They started monitoring these things live, like they were witnesses to space history. So this is one of his colleagues. They built a helix antenna for the 250 megahertz band, because that's where the US was doing Project Gemini. And they were listening to the astronauts communicating with the ground stations. Ultimately, this evolved into actual amateurs monitoring the Apollo program around the moon. And there's actually, if you go dig into it, Sven Garn he's not an amateur, but he's an amateur satellite observer. And he actually has recordings and notes, and he actually has a Doppler curve of I believe Apollo 17 in lunar orbit. They actually recorded audio of the astronauts communicating with Earth from lunar orbit on S-band in 1972. So that's pretty cool stuff. So, and the way they did it, when they look at the inverter that they had in the station wagon they rented, and all this equipment they gathered up, it was pretty amazing. Other things amateurs were doing early in the space program is they were monitoring weather satellites and whatnot. 137 megahertz was really, and still is, a very active satellite band. You can see the hardware here. It's pretty primitive. They had a tape recorder, and they're using an oscilloscope to look at satellite weather images. So they were, this was like amateur stuff back in the early 70s when these weather satellite systems got going. Nowadays, you can download software. A couple of colleagues of mine in Europe have written software called SatDump. I don't know whether you've heard about it, but you can actually, on L-band, S-band, and X-band, and 137 megahertz, you can download full color images, super high resolution weather maps and pictures from all these satellites, and quite a few of the science satellites as well. So all of this stuff has been figured out by amateurs and is now in the public domain. It's not just the province of space programs. So in the 1970s, as I alluded to, here's Greg. Greg's the guy in the background there with the glasses. So they're using their tube equipment. That's his backyard with his probably the first known S-band tracking dish for space stuff. Another guy, I think his name is Richard Flagg in the States, he also assembled a similar setup, and that was the one they used to monitor Apollo 17. So that's I believe one of the chaps that you see in a lot of the amateur radio handbooks with his pictures about monitoring the Apollo program. So you can start to see, and when you start to read some of the historical contexts of these chaps, a couple of them have written books. I know Sven has. I can't remember the name of the book, but ask me later. I can send you a link. I'll highly recommend it. He's a very technical guy, but his story is about, I'll sum it up and say, he's trying to teach people in the future how to take a front row seat to watch what we're doing in space. And his perspective, and so is mine, that what's going on in space is not the province of big corporations or governments. You know, they're the only ones that can afford to understand what's going on up there. Everybody in this room has the capability of doing it, and we have the capability of sharing that with millions of other people. So it's not something that's exclusive. It's not something that it can't be understood. So now we go into the dark side of space, pun intended. Hubble's in reverse. Why do amateurs look up? So what motivated these people in 1957 to look up? Probably the novelty, to a certain degree. There's probably a certain level of geopolitical stuff with the Cold War and whatnot. But as the space program got more developed and the various countries, the Soviet Union, the United States, and their allies started to get their space programs going, they developed their own space situational awareness programs. And they were able to, the governments were able to take pretty much complete control and start to give their own narratives about what's going on in space. And fewer average people like us were looking up. So that gave, particularly the United States, the opportunity to create whatever narrative they wanted, potentially. So the concepts of Hubble's in reverse are that we all know about the Hubble Space Telescope. Many in this room probably know a bit of the story of the Hubble Space Telescope. They made a big, beautiful mirror for it. They launched it into orbit, and then they realized, oops, we made a mistake. We didn't figure it quite right. We need to do some corrections. We sent some astronauts up and they fixed it. But it turns out that wasn't the only mirror that was made. There's been an ongoing production of these mirrors for another group of satellites that are essentially Hubble's in reverse. They're watching, maybe not us per se, but they're watching the adversaries of the Western world. These satellites do leave a trace. Their orbits are classified. Here you can see some of the evidence and sort of for the darkness of the frames. That little flare over there is an optical image of a keyhole satellite, a KH-11, which is the moniker of a Hubble in reverse. They're known as a series of satellites called keyhole 11s. Unfortunately, the Doppler curve didn't come out, but we can also hear them on S-band periodically. That in itself allows us to keep tabs on where they are. And a small group of amateurs around the world keep track of the classified satellites. And why do we do this? It's not so much to tattletale on what our governments might be doing, but the fact is our governments are actually doing something wrong. They've already agreed to publicly share these orbits, to publicly tell the world that these things are in space and what their purpose is and roughly what their orbits are. And our governments have chosen to withhold that. And which is not such a wise thing when your adversaries don't do the same. Russia, or the Soviet Union at the time, promptly published with the United Nations the purpose of their missions and provided the basic information they required under the Outer Space Treaty and the orbital disclosure conventions they're under. So what we've ended up at the present day is a situation where a lot of governments around the world aren't being completely transparent about what they're putting in orbit. And I'll get into that a little bit later because I don't want to go down a really dark path here, but I wanted to bring people's awareness to that. That's one of the reasons why amateurs do continue to look up and actually spend the time they do. There's a small group of us around the world that monitor these orbits by looking at little dots moving across the sky and keeping tabs of things that aren't in the public catalog. So here's a pretty good example. There's what the Hubble Space Telescope looks like, a nice high-resolution image. And there's an amateur, relatively high-resolution image of a Hubble in reverse. So that's I believe, USA 232 or some such. They're all given these code names. The United States issues just generic numbers to them. But these things are essentially telescopes, Hubbles, looking down, and they provide incredible resolution. Donald Trump actually released one of the only known public images from one of these satellites a few years back of an Iranian launch site after an explosion. So we get a sense of what they can actually see, and it's pretty amazing. In the 1980s, there was kind of the culmination of the Cold War. As part of that, this whole idea of classifying orbits kind of became a thing. It was somewhere around 1983, under the Reagan administration, that all of a sudden satellites started to disappear from the public catalogs that were issued by the US government. And what was noticed by amateurs over time, after numerous launches occurred, that it appeared to be related to a new basically surveillance satellite program called MISTY. MISTY was a stealth satellite program. So the first MISTY was launched on a space shuttle mission, USA 53, and ironically, no one in Europe or over in Eurasia saw the thing, but over North America, it was optically spotted, and amateurs started tracking it. And then when we started posting public information about that, all of a sudden, USA 53 disappeared. So I think what was going on there, and what is speculated in amateur historical circles, is USA 53 was a stealth satellite. You can see this diagram, which comes from a patent. The idea is that they created basically that surface, that kind of conical surface, was a set of mirrors or reflective surfaces. So when the spacecraft was aimed at Earth, it would redirect the reflected light from the sun in such a way that we wouldn't see it. The reflected light would go off into space. That's how they did their stealth. So they didn't activate or orientate the satellite appropriately over non-hostile areas of the Earth, and that's when amateurs picked it up. And then suddenly they started maneuvering it a lot, and it disappeared. It was picked up on and off for a few years, and then there was no more of it. Later, there was an even more mysterious launch and a whole lot of subterfuge. And USA 144 went up, and we believe this was MISTY 2. This mission was really weird. They launched the thing on a trajectory that it gave it an appearance it was going into high Earth orbit. And then there was an object that appeared in a weird medium Earth orbit. The Russians got involved, the Soviets at the time, basically saying something exploded up there, and poof, everything seemed to disappear other than this weird object in medium Earth orbit. If you know anything about orbits, you don't put anything in a relatively low medium Earth orbit of the Earth because it's right in the Van Allen radiation belts. It just kills the electronics, especially older stuff. So what was this thing? So amateurs monitored for a while, and we realized that it had a really, really low mass and was really affected by solar radiation pressure. So we assumed it was probably an inflatable bag, a decoy. So whatever they launched on USA 144 disappeared. And then we don't know whatever became of it. So maybe they learned their lesson on USA 53 and it just disappeared, or whatever. And we'll get into another story later on called Zuma, which ultimately led to Image. So then there was a whole bunch of stuff going on in the US Congress. Really big disputes about money that was being spent on this MISTY program or this satellite program. And there was a third satellite planned according to budgetary records. We don't know if it ever ended up in orbit or whether it ended up being, obscured in other things. But this is the reason why I bring this whole topic up is this is a major aspect of what amateur satellite observers are doing. Collecting data day after day after day on radio and optically, keeping track of what's going on Earth orbit so we can catalog and create a public record of the real history of space, not just what our governments want us to know about. Another really interesting satellite that was put into orbit that we are actively monitoring right now, we call it Prowler. It's the only object that we've found in orbit that has never been publicly acknowledged. And it turns out that this is probably the first clandestine satellite inspector in geo-orbit. It was launched on a US shuttle mission with another mission that was sending, I believe, a communication satellite up with it. And they used, or appear to have used, the kind of like subterfuge of launching another satellite to kind of veil the fact that they put this guy up there. And what they did with this thing is they just put it in a near geostationary orbit so they could drift it around and monitor and image and inspect Soviet communications and other geostationary assets. When it was done with its mission, they did something pretty sneaky. They let it drift around, and there's these like kind of gravity gyres, like these little holes in geo orbit. So if you let a satellite just kind of drift in geo, there's one that's over North America kinda, and one that's over kind of India. And eventually the gravity, your sun resonances will kind of suck your satellite in, and it'll just kind of die there. It'll just kind of stay there. So what the US did with this thing is when they were finished with it, they didn't want it over the Soviet Union where they could see it because the Soviets had a very active space surveillance system. They left it over South America and North America. And it wasn't really picked up and kind of figured out until the mission was finished and all the pieces started coming together. And there's I mentioned Ted Moselcan, Mike McCants. They spent, Mike's is out of Texas and Ted's out of Toronto. They spent quite a bit of research and their knowledge, and with a bunch of other amateurs through observation, we were able to put the whole story together. When you read their paper, it's quite fascinating how they were able to put all the pieces together and the scant evidence that we were all able to gather and trace it right back. So thankfully, this practice of classifying orbits seems to be becoming less and less a policy of Western governments. They still do it, but they don't do it to the extent that they were. During the last Trump administration, Donald Trump actually signed a presidential order to declassify most of the American military satellites in Earth orbit. And through that, a vast quantity of satellites that are obvious that are there became declassified, like a lot of military communication satellites, missile detection satellites and stuff like that. There are still probably 100 or more that are still classified. Those are the most secret type things, the NRO, National Reconnaissance Office, Earth observation satellites, the signal intelligence satellites, etc. So with that kind of background, it kind of gives you a sense of why amateurs are looking up. Initially, it was for that euphoria that humanity was looking and exploring in space, and then there's this period that, where it's more dark in the sense that amateurs were looking up because nobody was really telling the world the full truth of what was going on in space. And the other side of it is not so much political, but it's like, what's the real history? I know there's some people in this room that have worked in that kind of more concealed space program. All that effort, all that history needs to be documented somehow. And I think in the amateur community, there's part of it is just telling that truth. So this video might not show up very much or at all in the brightness of this room, but this is finding USA 161. So you can see, I guess if we dim down the lights, you can probably see this way better. In fact, at all. You can see a couple of twinkling stars there. Eventually, I zoom in to an object. The story of this is a keyhole satellite that disappeared on us, did something completely unexpected. We've gotten to the point with the keyhole satellites that we know when they do their maneuvers. We generally know what their shifts are. And why we know that is when their TT and C beacons would flip on, we would monitor for months at a time, watching where their telemetry tracking control beacons were, and we would see nothing, except at launch time. They'd launch for the first week or two of the mission, the tracking and control beacon would be on, probably as a redundancy, and after that they'd switch it off. And then it'd be just radio silence. Nothing, 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 nothing. Then maybe 9 months later, all of a sudden, on a Thursday morning, the beacon would flip on. And you would see all kinds of funky ground locks to ground stations, all kinds of activity. But I can assure you, by 5 p.m. Pacific time, that beacon was off again. So everybody had gone home, down at Vandenberg or wherever they control it. And then by Monday, the satellite trackers would realize, oh, where did USA 161 go? We're not seeing it in the orbit we just saw it in. Then the hunt begins. And that's the kind of the usual practice. They would maneuver, the satellites would have a low perigee, so they'd dip down fairly low so they get high resolution images. And then they'd have a relatively high apogee. A lot of these Earth observation satellites did that. And periodically they'd have to do orbital maintenance just to keep the perigees high enough so they didn't re-enter. These things are worth more than an aircraft carrier, just to give you a kind of a sense of their cost. So they would try to keep these alive as long as possible. What USA 161 was doing was, for the first time since we'd monitored these things since the 1970s, entered an entirely different orbital regime, and it stumped us for a couple of months. Literally, I was out on the pier in Roberts Creek every night over the course of an August and September. My wife can attest to that, wondering what I was doing, with a video camera in the dark at 3 in the morning, looking for this thing. And one of my colleagues came up with a hunch. He said, you know, I looked back at some orbital history of some of the earlier keyhole systems that used to use film. I wonder if they're using this orbit again. And he looked at the plane of that orbit, kind of made a guess about what they could have done and how much energy, and he said, look here. And that's what I was doing that night. I was standing there with a pair of binoculars with a video camera, watching in the relative area where the satellite should have appeared out of eclipse of the Earth and appeared to us. And as I was watching in my binoculars, and it's unfortunate you can't see it on the video, you suddenly see me grab the camera, because I saw it in my binoculars coming out of eclipse, this like little dot just getting brighter as it gets fully illuminated by the sun, as its sun rises. And then I see it, and I look down at the camera and I can see it on the camera. I zoom in with the zoom lens and start tracking it. Why am I doing that? You can see this timing at the bottom. You can see how accurate the timing is. That's fractions of a second. What we're trying to do is get its position in time, angularly, and make a number of positional measurements and try to get a long arc of observation so we can get that new orbit figured out. So that's generally the technique that we use to keep track of things that the powers that be would rather us not really keep track of. So there's other things that are much less political, much less polarizing than keeping track of intelligence and military missions. There are also things like keeping track of or becoming aware of the rhythms of the universe. And satellite tracking can also do that. You know, a lot of amateurs, I'm sure a lot of people in this room, if you ever had the inclination to track a satellite, the first thing you do is you download a piece of software, you download the most recent orbital elements, you hit real time on button on it, and it'll tell you, or it'll plot the infamous for you over the next day, telling you when it's going to rise and set, what its azimuth and elevation is going to be. Okay? But that doesn't really give you any insight into the orbit. Some guy that wrote the software had some knowledge about that. or used a bunch of defined functions or some kind of software that functions that he created his program with. But when you actually look and you just take back and you look long enough, you'll see things that are pretty amazing. So in the late 2000s, the early 2010s, NASA put the Lunar Reconnaissance Orbiter in orbit around the moon. And its job was to reveal the nature of the moon to us in high resolution over years. In other words, document and photograph the moon to allow us to really get a really good sense of what's there and how the moon changes over time. The NASA JPL engineers, the guy that runs it, the University of Arizona, the people that run this thing have been keeping it alive for a couple of decades now, and it's become one of the most ubiquitous assets in lunar orbit. So its primary mission is to map the moon. I used it for understanding orbits. One of the coolest things about LRO is it's on all the time. It's sending an S-band beacon, and it's communicating every orbit that it goes around the moon to a ground station down in Arizona. So as you can see here, this may look like you're looking at somebody's AM modulated carrier on 80 meters or something. This is a modulated orbit of the moon. So what are you seeing here? The x-axis is days, and the unit is modified Julian date. So each day is one increment in number. Modified Julian, we've just used an arbitrary date as our kind of like epoch, and then the reason we use it, we can use a fractional number. So it makes keeping tracks of dates really convenient. So you don't have to do, divide by 60, 360, remember all the details of that. You can just, you want to add a day to it, or you want to add a quarter of a day or whatever, the math is easy. So generally in satellite tracking and aeronautics or astronautics, we use modified Julian date. And then we have frequency on the y-axis. And I'm not sure whether this laser will work for me. Maybe not, it would be helpful. I'm pressing buttons. Okay, I'll use my finger. So when you look at that kind of sinusoidal amplitude to it, all the little lines in the middle are each individual orbital paths of the moon. So each vertical line is one orbit of the moon that I was able to visualize. Over the course of, and each gap is when the moon set on my station. So the satellite's still orbiting the moon, but I couldn't see it. And then the next day it rose, and I was able to copy more vertical lines. And if you look at each one of those lines, it's just a little S curve like this, showing each orbit of the moon. You see this little sinusoid of that orbit. But what's really cool here is that kind of envelope that goes around it. What's going on there? That's not something caused by NASA. That's not something caused by LRO itself. That's something caused by the fundamental nature of the universe itself. What it's revealing to us is how orbits work. And one of the most fundamental things is that once you launch something from Earth and it literally leaves the ground, it's no longer attached here. It's no longer rotating with us. It's now its own celestial object that's locked to the stars, essentially. It's not really locked to the stars, but if you imagine it like that, it helps you visualize. So its orbital plane becomes fixed. So if you're standing out in space, or floating out in space, I guess, looking at that satellite, and you can see a line of its orbital plane, that plane would always be in line with the stars at the exact same spot. It's fixed. The satellite is moving around the Earth because of gravity, but it's not rotating around the Earth. The Earth is rotating under the satellite. And it's really hard to see and understand when you're standing on the Earth and looking at something in orbit around the Earth. But when you're standing on the Earth looking at something in orbit around the moon, that becomes obvious. Why is that? The Doppler effect. So this diagram here, you can see the red lines. That's the orbital plane of our hypothetical lunar reconnaissance orbiter. as the orbit, as the moon orbits the Earth, that plane is still fixed to the same area in the sky, to the stars. But from our perspective here on Earth, as the moon orbits around the Earth, that plane changes. So why does the amplitude change? Because Doppler is related to the observed velocity that we're seeing here as the observer. So when the plane is face on, there's hardly any Doppler at all. You get the null, the low part of the envelope. When the plane is lined up with us, you get the big peak, and that occurs every fortnight as we see the plane of the orbit change in perspective. When I posted that on Twitter, there was a huge debate, like what's going on? Like what does that mean? And it was so fundamental, and it just revealed to me that just by having an S-band receiver and looking at something for 27.3 days, you're able to see a fundamental aspect of how the universe works. What Kepler figured out, what Newton figured out, people like that, like Galileo, all these guys that kind of put it all together. But amateurs can do the same thing by just looking long enough and reminding ourselves that that's how it works. That's how science works. You can't believe something until you actually see it for yourself. And when you see it, it becomes internalized. It's not some equation, it's not Kepler's law, it's real. So speaking of real, yes, there are angels in space. A few years back, the United States was preparing to launch another classified mission, another geostationary surveillance system. I was given some preliminary orbital elements by a colleague of mine and said, hey, Scott, you're going to be a good position, I think, to have a look here. Have a look. So they launched this thing, and of course, in typical military manner, it's a big acronym. The acronym doesn't matter. They launched this satellite. That was supposed to be the last we saw of it. It's like, bye-bye. About 6 hours later, I saw this little streak of light pass through my low orbit optical camera, and then I picked it up on S-band, a wideband signal from the rocket booster that's taking it up. I then did a little bit of orbital dynamics, figured out this plot over here shows you where that green line is basically where the geostationary orbit belt is. So I basically predicted its arrival in future orbit based on the Doppler and optical data, and then using the Doppler to kind of tune it in. And as it kept rising, I kept using the Doppler to make sure it hadn't done anything funky on the way. It shouldn't have. It will only fire its rocket when it gets up to circularized, but you never know. So what I was rewarded with was this. And I don't know whether the video is going to show up very well, but what you're seeing here is the sun was almost just about to rise. And I'm looking this is done with an 85 millimeter lens on a DSLR camera. And this is that little dot kind of over the head of the angel there. That's the rocket booster. And that big angel shape is the rocket booster venting all of its remaining fuel into space. So this is an animation of the circularization. If you look in the corner over there, eventually you'll see a little dot tripping across the screen. You probably saw that little plume there. That's the circularization burn. It's just deployed a satellite, deployed the next satellite, and now it's venting its fuel. And then the sun came up. So there are angels in space. They just happen to be launched by our militaries. The next night, I came back looking for the objects because they were supposed to put 2 little geostationary surveillance satellites in orbit, and was able to pick them up, and we kept track of them after that. So again, it's tales like these that led to this next story. So we'd gotten pretty good at finding things that we weren't supposed to find in space. And So this seemed like a normal routine mission for us. You know, it's almost like we're almost calling us out. So SpaceX launches for the US government some secret, undisclosed payload they called Zuma. And so I thought, okay, throw down the gauntlet, we'll find it. We can find everything else. Brought to bear the optical and S-band system, both the dish and the omnidirectional system. You know, I was pretty cocky, figured we'd have it picked up in a day or two. Well, no, they seem to have something else in store for us, and we still don't know what happened. So Zuma just disappeared, almost without a trace. And this is the level of detail that we go into. We kind of, through what they call notices to airmen and sailors, they post hazard warnings about where the rocket debris is going to fall. Even the most classified missions, they do that. It's a safety thing. You just can't have a rocket falling on a ship or through an airplane full of people. So they post these safety bulletins, and from those we can come up with notions of orbits or trajectories they're going to be in. So we knew what the initial trajectory of Zuma should be. And lo and behold, we had an airline pilot flying over Sudan that posted on Twitter this weird spiral. And the spiral was almost perfectly timed and positioned to be our Zuma. And then, not too long after that, SpaceX announces mission complete, where we've successfully launched what we were told to do. And then the US government releases some kind of notice that there was some kind of malfunction with the Zuma payload and that it had prematurely re-entered due to some sort of failure. Boy, was our spidey senses tingling after the story I just told you about the Misty satellites and how they just kind of ramped that up. We were all like, yeah, sure. So I looked at the trajectory that they put this thing into, and I wouldn't have been able to see it optically. It was not placed well for optical observation for anyone on Earth, just the way the orbit worked out. So we started searching on radio. So at the time I had a Blade RF1, which I just sold at the flea market to one of the chaps here. So you have that radio right there that was the one that discovered this. And I started looking 20 megahertz at a time on S-band. So listening for an entire day, then switching to another 28 megahertz, monitoring that whole swath for an entire day, looking for a Doppler curve of a satellite in low Earth orbit that we didn't have documented, that wasn't in the general catalog. Lo and behold, I came across a Doppler curve, but it wasn't in low Earth orbit. So initially I was like, not smiley face, just another anomaly. Just kind of noted it, wrote it down on my notepad, checked the data later. Boy, did I check it later. So I did my initial plot. It's like, oh, not only is that a satellite I haven't seen before, but it's also emitting data. Well, that's interesting, and it's a high Earth orbit. Wonder what that is. So we've got some software that can do Doppler analysis, compare a Doppler curve to a catalog of orbits, and I got a match. It came back to 26113, image. So what the heck was image? I thought. I did a Google search and came back to it's some kind of a rural study satellite that was in a highly elliptical kind of polar orbit. And I'm like, okay, that's interesting. And then I normally, anything new that I log that I wasn't aware of, I do a little bit of research into it. And it turned out to be very lucky that I did. I did another Google search about the satellite, using its name and whatnot, and I stumbled across a NASA failure report. And in the report, they were discussing image was, failed, not communicative. And I'm looking at the data that I had and I'm double checking everything, and I'm like, looks pretty unfailed to me and looks like it's communicating or trying to with somebody. And so I started monitoring more. I pinged a couple of my colleagues in Europe, had them look at my data. They're like, no, it looks good to us. Looks like that, And it turns out my buddy Case, and he starts looking through his archives and goes, Scott, I've got this carrier too. You're not the only one that's hearing this. So that night I come home and I'm sitting at the dinner table with my wife Laurel, and I'm telling her about this story, and she's like, kind of like, hey dumbass, why didn't you just email NASA and tell them you found their satellite? And I'm like, okay, that sounds like an appropriate thing to do. So I went back to my computer and used those same investigation skills to find the guy that built the thing. I sent an email to Dr. Birch down at a research center down in Texas and went to bed. I woke up the next morning and my life hasn't been quite the same since. Dr. Birch emailed me back and he's basically like, oh, this is very interesting, blah, blah, blah. And then I looked at his copy list and then I looked at my inbox. I'd usually have 4 or 5 emails there and there was probably 200. He had grouped all the former NASA engineers, all the people that had worked on this program in the past, and everybody was like, asking for more information. There was this kind of like dump of what. So over the next few hours, I started sending them more information, started coordinating with them, and within the next day or so, they actually literally wheeled a small little dish out in the parking lot of the Goddard Space Flight Center, and they actually sent me a picture. It's on my blog. And all these NASA engineers huddling around this thing, looking at a spectrum analyzer, aiming an image, and they're going, it's on. So they come back to me and they said, well, we're seeing a radio emission where image is in the sky on the frequency that image uses, but we got to decode it first. We need to see the spacecraft ID before we can. So that's where it got really interesting. So I was involved in the dialogue with all these NASA engineers looking for the doorstops and all these other things. Every engineer in this room knows what I'm talking about. After you've worked on a project, do you just dutifully take all the stuff for a project that's ended and get rid of it? No. It ends up on your desk, on the floor. Some of it might get thrown out in the junk and you take some home. Who knows? So all the NASA engineers were doing exactly that. They're like, oh, wait a minute, I've got the tape drive with the last bit of code that we wrote for that thing. Now we need it because it's not archived. So they're stumbling around trying to figure out how to talk to this thing, because I haven't talked to it in almost 20 years, and trying to figure out how to reverse engineer it so they could decode the telemetry and get it. So it took them a couple of days to get that sorted out, and then they got the spacecraft ID, and that's when it went really nuts. At that point, what was going on was they were attempting to reconstruct a control room, because IMAGE was a weird mission. It was one of the last of a series of them where they literally decommissioned all of the control equipment that they could have controlled that age of a satellite, because they didn't need it anymore. So literally they were going back to all these engineers that had worked on the program and rummaging through their offices looking for all the pieces and parts that they needed to reestablish a command station for this thing. So that was what was going on. Unfortunately, IMAGE wasn't so cooperative. Part of the recovery data, this is one of the plots that I sent them, it doesn't look all that overwhelming, but what this demonstrated is that the satellite was rotating at the same rotation period, almost the exact same rotation period of its operational state, which was rather unique, so many RPMs. And all the data that I sent them originally, that's what really twigged them. It wasn't just a Doppler curve that I was claiming a signal on this frequency. It was like all of this data that I sent them and the methods and how we did it that basically established to them, this is credible. From some guy that they'd never heard of before, sending them something. Like I sent them enough information, it was like, they're looking at it going, that's pretty credible. So was the image lost? No, it was just lonely. We still don't know what caused it to fail. The spacecraft failure report indicated there was some sort of kind of non-redundant circuit breaker issue that could cause the satellite to shut down its communication system and still be functioning, but just not able to communicate. And as it turns out, the satellite itself probably succumbs to that on a periodic basis now, and they figured that it would only take a full eclipse of the satellite and the battery eventually dying, that the system would reset and bring itself up. Apparently it took about 15 years for that to happen, and that's why I saw it. So here's what Dr. Birch sent me, and I don't know, I think a few people in this room understand what a mission coin is. I know Tony Bruno on Twitter not too long ago, somebody asked if they could buy a mission coin for one of their ULA launches. And Tori Bruno came back and said, you can't buy a mission coin. It has to be gifted to you by someone in the mission. And I came home one day and this was a little package sitting on my doorstep from Dr. Jim Birch. He was the lead principal investigator for Image. As part of my, was talking with the NASA PR people, and they asked me if they could do anything for me. And I said, you guys can damn well QSL. And it created a bit of stink within NASA. I got a couple engineers coming back, it's like, we don't QSL, and it's just like, no, it's like, that may be your policy, but that's not the amateur policy. I heard your signal, I sent you a report, I expect a card. So after much to do, I got what I think is the only QSL card that NASA's ever sent to anyone for a signal report. So, and I had to go, remember those old utility shortwave monitoring magazines where you'd send a QSL card? And guys, that was a hobby, a big time hobby back in the day, where you'd send cards to utility stations all around the world that you'd heard on shortwave, and the radio engineer at the station would usually QSL. And it was a big thing. And that's what I likened it to them. It's like, guys, this is the free PR for you. If you guys actually responded to this kind of stuff, it's like, it creates, you'd have kids looking at this stuff, you'd have all kinds of people getting more involved and active in it, and you'd be like creating a really good vibe. So hopefully NASA picks that up at some point, but I just thought that you guys would appreciate that one. So it wasn't a Hollywood ending for Image, it turns out. About a month after recovery, we were continuing to track it, and I was actually working with a couple of contractors that had built the satellite, because we were able to provide them more continuous monitoring than their assets were. And then we started noticing the signal was breaking up. And as the sun angles changed on Image, we believe what was happening, because it wasn't maintaining its attitude correctly, that it overheated and it forced it to shut down again, and it latched off. So it probably the same issue that probably took it out the first time, that we observed it again. Since then, I've seen it come back once or twice. NASA itself has been periodically monitoring it. I don't know whether they still have active people on it, but there was about a year after the recovery, they still had engineers that were still working it. Why? Image was a real big thing to them. It was one of the most useful satellites for the buck that they launched back in the day for monitoring auroral stuff, and it provided them with more insight about the aurora and the space weather environment around Earth than many other missions combined at that point. So it really left a very positive vibe in the whole NASA community, from what I understand. So when they thought that they could get it back, it's like, I don't know, there was a geek resonance that occurred. It just sent a spark through NASA and JPL, and they were just like, we want it back, we can get it back. Okay, so Image, it failed like 20 years ago. We talked about that whole little drama. Well, what about we went back further? Through my escapades of monitoring space, I've seen stuff and be able to kind of re-establish kind of a timeline of how pretty much how the US military and the Russian military has used radio and communication with their satellites over the decades. A lot of that work was done by earlier colleagues to me, but fortunately, the United States builds pretty darn good satellites that just refuse to shut off. And so what we're left with is a whole bunch of space junk that's still emitting. What does that tell us? We can see that the communication systems they've used have been consistent since the late or early 1920s or 1970s to the present. So their frequency usage for the type of mission, the emissions, probably even to a certain degree their encryption standards are quite similar for this period of time. So it kind of makes you wonder, like, wow, that sounds like, why would they keep using the same stuff for decades at a time? Well, it must work. It must be damn reliable, and it must keep budgets down, you'd think. So where did all this stuff come from? So back in the 1960s, there was a satellite band. Everybody's probably heard of the 137 megahertz band. You can find weather satellites there and just below 2 meters. But there's also a band at 236 megahertz that was a couple megahertz that was widely used in the 1960s by satellites. So if you're looking for old, dead, quote unquote, emitters that might have historical significance, then you need to find bands that are where satellites that were launched may still be using them. So it turns out a few years back, an amateur in the UK, and his name just gapped out of my brain right now, he discovered LES-1 on the 237 megahertz band, still emitting from 1965. So I'm thinking, sounds like a happy hunting ground for zombie satellites. So I built up this little wooden Yagi, and this COVID had just begun, so I had some spare time after running out of gardening tasks. So I built up this little Yagi, put it on the roof, aimed it at where LES-5 should have been. So LES-5 was the first experimental UHF tactical communication satellite for the military. So they launched it into an almost as high geoorbit, but it would drift. It drifts from west to east over the course of a few days in our window here. If you're standing here, it would take a few days for it to go from west to east. So I happened to catch it just before it was going to set in the east. I aimed my antenna that way, just started tuning around. So this is what LES-5 looked like. It looks like a big garbage can with solar panels, and it wasn't really, you can see this very happy technician standing beside it. It doesn't look all that impressive. But in this thicket of UHF noise, there was a PSK carrier, something sending data. It wasn't noise. I could actually get lock onto this and see a constellation forming. And anybody that's played with PSK 31 or anything else will know exactly what I'm talking about. So I got kind of excited. It's like, whoa, how often do you say, you kind of like go looking for something that's 50 plus years old, and there it is, emitting away. And it's like, okay, how do I prove this? Okay, it's not like image. A satellite in geo-orbit, you can't do a Doppler curve on it because it's fixed in the sky. And its Doppler curve is highly affected by things that are not modeled in normal satellite tracking programs. So what I had to do was time it passing through eclipse. So its position in the sky would become evident to me by when it got eclipsed and when it went out of eclipse. This is one of those moments where you only had one job. LES-5 had a battery, but its only purpose of the battery was to turn the satellite off. So if it passed through eclipse, its radio transmitter should shut off. When it come out of eclipse, it should have switched back on. And that's exactly what it did. So this plot shows the satellite carrier disappearing at the beginning of eclipse. The minute the eclipse ended, it came back on. Sent an email to one of my colleagues in Italy, gave him the data, said, have a look, because I knew he had capabilities on this band. He did the same experiment the next night, and he had the same result. So I'm like, we've recovered LES-5. This thing was launched in 1967. And as it turns out, it was, for an old guy, it was pretty coherent. It wasn't slurring, it wasn't rambling, it was sending telemetry. And interestingly, it still had an active experiment running on it. It had a radio frequency interference experiment where it monitored all of what is UHF SATCOM right now, the band that's used by the US military. One of the purposes of this satellite was to kind of make a map, a radio frequency interference map of how that whole area of spectrum was used all around the world. That experiment was still running when we tapped into it. What you're seeing here is actual telemetry that we decoded from the satellite, and this is the telemetry frames related to its orientation, its attitude control. And you can see that by the angle there, and that is the Earth sensor, that parabolic part. And what it's showing us is the satellite was wobbling. It wasn't holding attitude quite well, but it was holding it well enough. The way the antennas worked on it, it spins, and the antennas were phased in such a way that it would only be the antennas that were facing Earth that were being energized. And it also turned out, I'm not showing it here, but we were able to figure out the power converter channels based on an old paper that we found that showed us that they had found a problem in 1967 with the power converters, and lo and behold, that problem was still there. The data was almost exactly the same, and we were able to identify the 4 power converter channels for the solar panels. Of the 255 data channels, I identified, I think, 150 of them before the satellite, about a year later, became incoherent. We weren't able to decode the telemetry anymore. Something had finally failed in the satellite, preventing that. So just to prove that I'm not just after the NRO and the military in the West, China has an interesting habit of launching things into space now, and they're not exactly the most transparent as well, for different reasons. So we're going to talk about how China went to the moon, and back, then beyond, and then back again. And it turns out, and beyond, really beyond again. So Tianjin 5. So Tianjin 5 was the first Chinese sample return mission that went to the moon. So big hubbub all around the world. China was going to the moon to grab some rocks and come back to the Earth, to be the 2nd or 3rd nation to do that. So they put this thing on the biggest rocket they have, they send it to the moon, but they don't really say anything other than that. They don't release trajectories, they don't release much information about it. So the amateur tracking community was really left, what do we do? And I said, well, you aim your S-band antenna, your X-band antenna at the thing, you collect Doppler, you start timing stuff. So I spent the next 3 weeks of my life reverse engineering the mission profile. So what did Tianjin 5 do? Well, it pretty much, what happened was, there was a leak out of China. So as you could probably imagine, the people in power there would probably consider this something like a spectator sport, and they would probably come to conferences, and they would want to have summarized information given to them about what's going on with the mission. It turns out that they had a pamphlet of the mission to the moon, and in the pamphlet they didn't give you really a breakdown in time when everything happened. They gave you these maps or plots like this, where they showed the orbital dynamics, when they were going to arrive at the moon, how many times they would orbit, and all that kind of stuff. So I was able to take that leaked pamphlet and reverse engineer a timeline to the mission that followed the mission within 10-15 minutes for most of it. And what we weren't able to figure out from that, we were able to figure out from the Doppler. And then we were able to keep track of that mission until it left the moon, came back to the Earth, and then it performed the maneuver to drop the re-entry capsule, collected the rocks in China, and then they sent the propulsion module out to the Earth 1 point. And that's what this picture is from. So it goes out to the Earth Sun L1 point, which is like this little, where the Earth's and Sun's gravity kind of equalizes, and you can place a spacecraft there and keep it there with minimum fuel. So they demonstrated they could send their satellite there. It's the first time China did that. Good stuff. They made a press release, they published a photo of the Earth and the moon, and everybody was like, oh, great stuff. Okay, so then nothing was said, and nothing has been said since. So we sat there, diligently monitored its X-band carrier, and then one day I looked at the spot, there's no carrier. Looked around the spot, no carrier. Started really looking around, and after a couple hours I found it again, angularly way out of the way. So at that point I alerted the other amateurs in our group, and we started monitoring it. We got some asteroid observers involved, and before long we were able to get a trajectory, and then one of our analysis in the group comes back and says, hey guys, it's coming back to the moon. It'll be here on September 14th or thereabouts. So on that date, I couldn't see the moon because it would be really low in the sky. So I went on a rover mission with my X-band dish down to the beach, where I had a nice panoramic view of the horizon to the south, set up my dish and waited for it to arrive at the moon and watched it paraloon to the moon. And what I watched was actually something really beautiful. They didn't fire the rocket. There was no perturbation in the Doppler curve. They surfed lunar gravity and placed the spacecraft into a high Earth orbit of the Earth. And the beauty of this didn't become apparent to me until some more asteroid observers have made some position observations that it was coming back to the moon in 3 months for another rendezvous. So lo and behold, we set up, the weather's horrible for all of us. We monitored on Doppler. They do another arrival, paraloon at the moon, where if they were going to enter a lunar orbit or something like that, they would have fired the rocket and we would have seen it in the Doppler. They didn't. There was no evidence to us that they just did looked like a flyby of the moon. It's like, why would they do this? Maybe they're just practicing or whatever. So we lost track of it again. A month went by, we're searching for it. One of my colleagues in Europe sends out a notice, I found it. And it's near the moon. And then we started tracking it and we realized it was near the moon, but it was in a very unusual orbit. It was in a distant retrograde orbit. The first time man has done this. And interestingly, we might have all watched the Artemis 1 mission, the first test mission to the moon of the new SLS rocket and the Orion spacecraft. It was supposed to be the first object to go into a distant retrograde orbit. And the Chinese had quietly scooped them. They'd gone there and done it first, and they didn't say a word about it. So Tianjin 5 remained there, largely just orbiting the moon in this very bizarre three-body orbit. And then all of a sudden, before Tianjin 6 launched earlier this year, back in May, they got tossed out. And the interesting thing, we knew it was coming because we noticed it made a small maneuver about 6 months, 9 months earlier. And when we modeled that maneuver, it destabilized its orbit. It's a chaotic orbit. So basically, it destabilizes itself as like taking a top that's spinning and just tapping it just very gently, and it starts to wobble. And eventually that wobble picks up and then and flipped itself right out of the Earth-Moon system into an orbit of the sun to dispose of it. We watched it as it sailed away, and it switched off its radio transmitter. Like we literally saw the moment when they pulled the plug. And then a couple weeks later, they launched Tianjin 6 using the same radio frequencies. So China had demonstrated the ability to literally surf around the Psi-lunar system with this spacecraft, and they kept it quiet. We wouldn't know it unless amateurs were looking. So here's a good one. Yep, I'll pick it up here. So here's a good one. Aliens and hollow threats. So I'm sure a lot of people heard about the potential detection of alien life from Alpha Centauri a couple of years ago. The Parkes Radio Telescope, through the Breakthrough Listen, had a leak come out from somebody in their team that they had detected a fairly decent SETI potential coming from Proxima Centauri, sorry. So, and they actually made a statement about a radio frequency, 982 megahertz. So that intrigued me. I thought, well, more likely it's probably a satellite. So I went searching. Lo and behold, I found not only one, but 3 satellites on or about 982 megahertz. Turns out those satellites weren't from aliens. They were from Russians. And it turns out that the orbit that they were in wouldn't have allowed Parkes to see it. But something dramatic happened anyways. We noted all this, we looked back in history, and we found out that the Russians were using that radio band for a transponder system to communicate with their intercontinental ballistic missile system from the 1960s on into the early 2000s, when they discontinued the Molina communication system. So time goes by, and the Russians decided to knock on the door of one of their neighbors and come uninvited into their country. And they made certain comments in the public that, don't screw with us, we got the nuke. So I turned my antennas back to their meridian system, and I happened to notice 2 were missing. And so I saw a post from Rogozin, who used to be the head of Roscosmos, making a blustery statement about the glory of Russia, and they were going to launch all these satellites into orbit as a response to Western sanctions. So my comment to him, my advice to him was, I think the first thing you guys should launch is a couple meridians to replace your missile communication system to make your nuclear threats credible. He actually responded to me, as you can see. So we had a little dialogue, and then I wrote up my results and posted that for the world to ponder. So we'll quickly go through the successful failure. Here's a little EME action on 13 centimeters. That was a carrier from the DSN trying to recover Virpan 1 lander that crashed on the moon. India launched its response after the failure, and this is the complete Doppler curve profile of a mission to the moon and a landing. Launch, and that little stub of over there is some lunar Doppler of the lander sitting on the moon. So that's the kind of observations that I do, and I compared it to all of the public data that India released about the trajectory. So you can see, unlike the Chinese missions to the moon, the Indians were releasing all this information per the UN Space Treaty, Outer Space Treaty, being transparent about what they're doing. So, oops, kind of a wagging the dog. So in the private sector, we also monitor that too. Last year, the company Viasat launched a very expensive new satellite called Viasat 3. I wasn't really paying attention. I don't really pay attention much to the commercial systems. And I got a couple of messages from people saying, hey man, you should look at Viasat 3. So I looked at Viasat 3. I looked at it and copied some data from it. The telemetry beacon was loud enough that we could probably decode it. Had a colleague of mine help me do that. And we saw this weird ASCII message. First of all, why are we decoding anything from a satellite system that was recently hacked by the Russians over Eurasia? Why are these guys sending anything in the clear? Why am I seeing ASCII text in their data? And to make it even weirder, it turns out by looking through GitHub, we were able to find the code that this thing was doing. It was doing a geometry, a sum squared difference analysis of some structure using a file format called PLY, which happens to be a polygon file format. So what they were doing is they were trying to characterize the geometry of a large reflector. And they were doing this over and over and over, day after day after day after day. So you would think that, why would they need to characterize the geometry of something they deployed so many times? So it turns out, I made a public statement about what we were seeing. All the stockbrokers went crazy, and I learned a valuable lesson not to do that again. And it turns out that we stimulated Viasat to actually make a public statement that they couldn't hold it in any longer, that their satellite antenna for this $500 million satellite had failed to deploy properly, and they were having problems. So I hope through going through all of this stuff, giving you a sense of the stuff that I do in a more non-technical way, but trying to give you a sense of where our mindset is at. A lot of us are not doing it for highly political reasons. Our main focus is the transparency aspect, that space belongs to all of us, it belongs to all humanity, it belongs to no one. I consider it kind of the ultimate international park, and if we treated it like that and thought of it like that, then I think humanity would be way better off, because it would probably give us a place where we could all be equal and share something great, and hopefully make for more of a peaceful world down here. Any questions?
I like your VHF Yagi.
You like that? Those are awesome, aren't they? I have so many of those. Is that the guy? Oh wow, you are the man. Those are, do you know Paul Marsh over in, he's another satellite observer that put me onto that. And I've been building those things since I was a teenager. They are like the universal antenna. I've actually made H-frames up with them.
Scott, we got it. Going.
Thank you, guys.
Thanks, Scott. We'll have to schedule a bit more time next time. So we got to get this on a roll.